Okay, so I think we'll begin the session. Hello, everyone. This is Tanya. I'm one of the TAs assigned to the aircraft design course taught by Professor A.K. Ghosh. So we will go over the assignment questions of week 5 and some practice questions for week 6. And we'll get back to the question that we half did last time, the one about neutral point. Okay. We'll do that towards the end of the session. We'll start with week 5 questions. So during a flight, if the aileron is deflected with a certain positive angle, how will this affect the lateral? Will it increase? Will it decrease? Will it remain unchanged? Or you cannot say anything about it. What will the right answer be?
Unchanged.
Unchanged. Tell me why. Unchanged is the right answer. Can you tell?
Because it doesn't change the CL alpha term. It doesn't change the slope.
Slope of the CM alpha, right? Stability is CM alpha.
Yes.
Yes.
Yes. Okay. So none of the control surfaces have anything to do with stability. It only enables you to control the aircraft. The elevator, the aileron, the rudder, none of them affect the stability no matter they're deflected or not. They only help us to control the aircraft, control the three motions about the three axes of the aircraft. They do not affect stability, however we deflect it. What affects the stability? For example, if it is longitudinal stability, like the CM alpha curve that we were talking about, what would affect the stability? So your curve is this, right? CM versus alpha is this. So what would affect the stability? What would change the slope?
Different aerofoil.
Different aerofoils. Anything else? So what, for longitudinal stability, what is the structure that we have incorporated into the aircraft? If we have just a wing, will we, sorry, I didn't hear you.
Horizontal stabilizer. Horizontal stabilizer.
Yes, yes, absolutely. And for lateral and directional stability?
For
Vertical
directional, we have
stabilizer.
vertical stabilizer.
Vertical stabilizer.
Okay, okay, yeah. So you need to keep in mind that none of the control surfaces affect the stability of the aircraft in any direction. It only helps us control the angles or control the motion of the aircraft, okay? So it does not affect stability. Next question. The aileron control effectiveness depends upon lift curve slope of the wing, lift curve slope of the vertical tail, lift curve slope of the horizontal tail, none of these. What would it be?
First option.
First option, because the aileron is present on the wing. So what is the control surface on the vertical tail?
Rudder.
On the vertical tail, rudder. Okay, yes, yes. So this is the correct answer. And what about horizontal tail?
Elevator.
Okay, so I'll just write that down here. This is rudder and this is elevator. Okay, so the contribution of vertical tail to directional stability depends upon. So in the first question, you answered that vertical tail contributes towards directional stability. So what is the contribution? It depends on, does it depend on vertical tail volume ratio, upon the efficiency factor, or both of them?
Third option.
Your voice is breaking, but I think you said third option. It's right. We'll just look at the formulae.
Yes, no, third option.
So C and beta, what gives you directional stability? So directional stability depends upon C and beta. For longitudinal stability, we had for longitudinal. We had CM alpha. For directional stability, we have C and beta. Okay. So this is the equation for C and beta, and you can see in the equation that there is this vertical tail efficiency factor, vertical tail volume ratio, Cy beta. This is akin to Cl alpha. So this is something similar to horizontal.
That's the coefficient of yaw and coefficient of yaw.
This is coefficient of lift. That is the slope of the lift curves graph, right? So this is something similar. You're right. That is correct. This is rho epsilon by dou alpha. So this was CM alpha's equation. Something like this. It's not the exact thing, but this was the contribution of the horizontal tail towards CM alpha. This was the equation. So this is analogous to it. So you have a vertical tail volume efficiency factor, vertical tail volume ratio, Cy beta, like he said, it is basically the lift curve slope of the vertical tail. Okay. So in that case, since the vertical tail is in the y direction, you have the force is called side force. It's called Cy beta. So Cy beta is nothing but dCy by d beta. The angle of attack that the vertical tail witnesses is the side slip angle. It does not witness the alpha. So that is why we have Cy beta. And this epsilon in the case of longitudinal motion was the downwards. A similar factor here is represented by sigma. Okay, so the correct answer, it depends on both the efficiency factor and volume ratio. Okay. Primary control for adverse yaw recovery. What is the primary control for adverse yaw recovery? Is it rudder, aileron, elevator, or throttle?
Rudder.
Rudder, yes. So anything to do with yaw, you use rudder. Can anyone tell me what is adverse yaw?
Roll induced yaw.
Roll induced yaw. Why does it happen? Every time we roll, do we have this adverse yaw?
No.
Yes, ma'am.
Okay. Someone who said no, can you tell me why you think it's not there every time we roll? We'll just discuss here. I'm not saying anyone is right or wrong. We'll just have a discussion here. So if you can try to tell me your reasoning. Okay. So I think I have a video here that shows you. Yeah, show you this. Can you hear it? Is the audio available? Can someone hear the video? Is the audio of the video, can you hear it?
No, ma'am. As such, no audio was coming. Maybe.
Let me just try sharing it again.
Aeroplane in straight and
Can you
level
hear it now?
flight.
Yes, ma'am. Now it's audible. Now it's audible.
Okay, so this will just show you what adverse yaw is. So then we can see if it happens every time or only at certain occasions. Okay, so just see this video.
An aeroplane in straight and level flight has a lift distribution pattern that looks something like this. The lift generated by one wing is the same as the lift generated by the other wing. Deflecting the right aileron down causes an effective increase in the wing's camber and an increase in the effective angle of attack. The lift from that section of the wing increases. Deflecting the left aileron up causes an effective decrease in the wing's camber and a decrease in the effective angle of attack. The lift from that section of the wing reduces. The primary effect of aileron deflections is a roll. This is an approximate drag distribution pattern. When the ailerons are deflected, extra drag is generated by both wings. However, more drag is generated by the downgoing aileron than the upgoing aileron. This is induced drag, and it is caused by more lift required on the right wing to help initiate the roll. Combining the lift and drag effects together creates the undesirable tendency for the aeroplane to roll in one direction, but yaw in the opposite direction. This effect is called adverse yaw. This effect is most noticeable at low speeds and on aeroplanes with high aspect ratio wings. There is another reason for the adverse yaw that is not often mentioned. In straight and level flight, both wings encounter the relative airflow head-on. But as the aeroplane rolls and the left wing moves down, a small amount of additional airflow strikes the wing from below. As the right wing moves up, a small amount of airflow strikes the wing from above, and vice versa. So as the aeroplane rolls, the relative airflow is deflected slightly up on the right wing, and the relative airflow is deflected slightly down on the left wing. As lift always acts at right angles to the relative airflow, the upward deflection of the relative airflow on the right wing causes lift to deflect backward. Conversely, as the left wing goes down, its relative airflow is deflected downward and its lift is deflected forward. The slight deflection of both lift vectors results in an adverse yaw moment to the right. The adverse yaw moment is felt when the aeroplane is rolling, and it stops when the aeroplane stops rolling. Adverse yaw can be prevented by using the rudder to create a yawing moment that helps to turn the aeroplane in the correct direction to remain coordinated. Some aeroplanes incorporate design features to minimise the adverse yaw. One such feature is called differential ailerons. By excessively deflecting the upward aileron, drag is increased on the downgoing wing. This produces a desired yaw force in the direction of the turn.
So now can you tell me if this adverse yaw happens every time we roll?
An aeroplane in straight and level flight has...
Can you tell me? I think somebody said it doesn't happen every time. Can you tell me now? This,
It does happen every time.
yes, because this differential lift and drag distribution happens every time we roll. It is more pronounced in certain types of aircraft like the high aspect ratio, but it happens every time we roll, which is why we also have to deflect the rudder when we roll. Okay, is that clear to everyone? Rudder is the right answer for this question. Like rudder is what helps in negating the adverse yaw effects. But is it clear that it happens every time we roll? Okay, so I'm guessing it is clear. So we'll move on to the next.
Yes.
Okay, thank you. This question has been dealt with multiple times. So which placement of wing has least lateral stability? High wing,
Low wing.
low wing. And can you try to tell me why?
And there is a diagram for this low wing configuration in which air moves the rolling down wing into downward direction and the upgoing wing into the upward direction. Hence, it increases the roll angle more and more.
Absolutely right. So what he said. So let me just try to explain that. We've done this. So if this is the low wing configuration, and yeah, so if it is rolling towards this direction, there is an impingement of the oncoming velocity in above the lift, above the wing, and there is one force here which contributes to further rolling motion. Okay, it does not generate a negating moment which would restore the equilibrium. It generates a moment in the same direction, so the aircraft continues to roll. But if it was high wing, rolling in the same direction, it would have, the impingement would be in this direction. It would generate a countering moment. It would regain the equilibrium. Okay, so high wing is more stable, low wing is least stable. Okay,
Ma'am,
Yes, yes.
what about mid-wing, ma'am? I have never seen any diagram for it.
Mid-wing is just a balance between both of them. So if you have something like this, and impingement in this direction, impingement in this direction would be the same, right? So it would kind of balance out. So there would be some force here, which would be balanced by the force acting here. Okay, it would be somewhere, its effects would be somewhere in the middle of both of them. So it's neither extremely laterally stable, neither is it poorly laterally stable. So these forces, the differential forces, would kind of balance out. Okay, so it would remain in that position. It would not create any restoring moment or any adverse moment. Does that answer your query?
Yes, ma'am, got it.
Yes. Okay. So what about longitudinal stability? Which wing configuration do you think would be more longitudinally stable? In the longitudinal direction, that is in the pitching direction.
Low wing.
Low wing. Can you tell me why? This is low wing configuration, and assume your CG to be somewhere here. And let's have a high wing here. Okay. So your lift force is here. Lift force is here. Okay. Again, CG the same direction. Can you tell me why low wing would be more longitudinally stable? That is the right answer. Why would it be more stable? This is low wing. This is high wing. Can you tell me?
I don't have a explanation much of it. I just know it as a fact.
Okay. Can anyone else try to, from this diagram? So I'll just give you another clue. It has something to do with drag. Okay. Now, can you try to justify why the low wing is more stable?
Oh.
Just try. Stability has to do with moments, right? So if
Yeah, it's because like if you draw the CG center line, if high wing, the CG center line is below that one, and in the low wing center line is, so the movement which is created is just balancing.
yes, exactly. So in the low wing configuration, the lift forces produce the same direction moment. Okay. So both of them have this moment, which is destabilizing in nature, which is why you need a tail for longitudinal stability. But in the low wing configuration, the moment that the drag produces is restoring. It's restoring. Okay. Here, the drag also produces the moment in the same direction. Both are destabilizing. Okay, see here, since the CG is, the wing is below, it produces a restoring moment about the CG. Okay, so this is slightly more longitudinally stable than the high wing configuration. Is that clear? Okay, so let me just try to explain that again. If your oncoming velocity is here, so if this is your disturbance, alpha, right? You need it to come back to equilibrium. You need it to come back to 0 alpha, if that is your equilibrium point. So you need a restoring moment that will create nose down, right? But if it is a high wing, both your lift and drag are giving nose up moment, which is further aggravating your problem. You don't have any restoring force. But if it is low wing, you have the drag force moment in the restoring direction. So this is slightly more longitudinally stable than the high wing configuration. Is that clear?
Yes.
So what do you think would be an ideal, not ideal, but relatively better configuration overall when you consider both longitudinal and lateral stability? For lateral stability, we
High
need
wing? High wing?
so then you have a compromise with the longitudinal stability, right?
Ma'am, actually, as far as I know, what is done is low wing with a dihedral angle.
Yes, yes. So that is one design aspect where you can have both longitudinal stability and
Ma'am,
lateral.
but we can also use anhedral high wing.
Anhedral high wing, will it contribute towards lateral stability? It would be adverse in the lateral stability, right? Think about it.
Ma'am, generally in cargo aircraft, anhedral high wing is used.
Okay. So I'm not sure if this is right, but won't the high wings still have a poor longitudinal stability, even if anhedral is introduced? I'm not sure, I can be wrong, but just try to tell me. So when he says anhedral high wing, it's something like this, right? You are right. I have seen cargo aircrafts with this thing, but won't it still be? It will not contribute towards longitudinal stability, right? Even if you introduce an anhedral angle.
No idea about this.
Okay, so let's look into this next time. Okay, so just remember this. Why do cargo aircrafts prefer anhedral high wing configurations? Okay, so we'll look into this next time. I'm not sure about it either, but I don't think it will contribute towards longitudinal stability, but we'll look into this. You also, all of you just look into this next time. We'll discuss this, okay? Okay, moving on. For a conventional aircraft, the sign of CL delta A and CN beta are respectively what? What is CL delta A? What is CL delta A, CN beta? Are they? Okay, so before we answer this question, we'll just go a little bit into directional and lateral stability. So for directional stability, what are the conventions? Right wing back, that's called a positive. That is our convention. Right wing back is a positive yawing moment. Why? Because your z-axis is considered downward, right? So your aircraft, cap is something like this. We have wings. So this is your positive x-axis. Y-axis is in this direction, and z-axis is considered down. Okay. So if you have your right hand thumb rule, right wing back is considered positive yawing moment. Yes? Is it right? Yawing towards the right, that is right wing back, is positive yawing moment. Okay. That is the convention we follow because we have assigned our z-axis in the downward direction. Then, if your relative velocity is on the right, we consider it to be positive side slip angle. So if this is your fuselage reference line and your relative velocity is in this direction, is on your right. This is the oncoming velocity. Then this is considered positive beta. If it's on this side, it's considered negative beta. Okay, this is our convention. Now deflecting your rudder to the left, that is positive delta R. That is our convention. Why? So again, this is your fuselage reference line. You have a rudder here. If you deflect it towards the left, which direction will the force be?
Towards the right side, ma'am.
Towards the right side. Okay. And which direction? This is your Y force, side force. Okay. And which direction will the aircraft turn?
Left.
Left, it will turn left.
So this is your CG. It produces a moment like this. So your aircraft turns in this direction. Okay. So that is our positive rudder deflection. Deflection towards the left is considered positive delta R. Okay. For static directional stability, what do we need to have? So if you're induced beta, this is your disturbance. If this is your disturbance, you need to negate this disturbance. So if you have a positive beta, you need to make it 0, considering 0 to be your equilibrium. 0 is the equilibrium. So if you have a positive beta, you need to make it 0. How do you make it 0? You turn your aircraft in this direction. So you need a right yawing moment, a positive yawing moment. So for that, what do? You have to generate positive moment, right? So for a positive beta, you need a positive yawing moment n, denoted by n. So your Cn beta, which is dCn by d beta, should be positive. For a positive change in beta, you need a positive restoring moment Cn. Okay. So for static directional stability, your condition is Cn beta should be greater than 0. Okay. This was one part of the question. For a conventional aircraft, meaning for a stable aircraft, Cn beta should be positive. Okay. So that is one. This is just the formula for Cn beta, which we have seen in the previous question. So if you have a positive beta, the generated force, so if you have some y here, because of a positive beta, the oncoming velocity is in this direction. You have a force generated in the negative y-axis. You have negative y, and the moment produced is, so you have a negative force there, which is why your Cy beta is negative. Okay. But the moment produced is restoring in nature, right? It produces restoring moment, which is what we needed. So the vertical tail produces the restoring moment. But Cy beta, because of the negative force generation, is negative. So when you derive this equation, this is why there is a negative sign in the final equation as opposed to Cm alpha. Cm alpha was just horizontal tail, Cl alpha 1 plus dou epsilon by dou alpha. There was no negative sign here, but because we need this to be restoring moment should be in the same direction, we have introduced a negative sign here. Okay. This ensures that your Cn beta is always positive for a stable aircraft. This is positive. Now, what are the components that contribute towards directional stability? They are vertical tail, which we just saw, it generates a negative force but produces a restoring moment. Similarly, a swept wing configuration also has a Cn beta positive. Why? So you have, this is your fuselage reference line, and you have swept wing here. Because you have a positive beta, and you have the normal forces here, right? So normal impingement of velocity, the normal component is by multiplied by a factor of cos of the sweep angle. Okay, so the drag on this right wing increases as compared to the drag on this wing, because this is facing the direction of the velocity. So because this drag is created, there is an extra drag here as compared to this wing. It produces a restoring moment. Okay, so this makes your positive beta 0. It helps in making your positive beta 0. So both vertical tail and swept wing configurations help in directional stability. Okay. Now, as far as direction control is considered, we have seen the positive delta R deflection, that is towards the left. So this is your positive delta R deflection. This produces force in this direction, produces a moment in the direction that we do not need. So positive beta, positive delta R, I'm sorry, positive delta R creates negative moment. Negative moment. So your Cn delta R equal to dou Cn by dou delta R will be negative, because for a positive rudder deflection, you have negative Cn being generated. Okay. So this is just a comparison between the two cases, longitudinal and directional. For static stability in longitudinal direction, we require Cm alpha to be less than 0. But in directional case, you require Cn beta to be greater than 0. For trim condition, for trimming at a positive angle of attack, we require Cm not to be greater than 0. But since our vertical tails are almost inevitably symmetrical and we require to trim at 0 degrees, your Cn naught is almost always 0. Control Cm delta E was negative. So for positive elevator deflection, you had positive moment being generated. you had negative moment being generated, which is why your Cm delta E is less than 0. It is similar for the directional case. Okay. Now we move on to lateral stability and control. In this case, the convention is when the right wing goes down, it is positive roll. Okay. So you have like this. This is the positive roll. Why? Again, because your x-axis is considered in this direction. So this is your x-axis. When you have your right hand thumb rule, rolling towards the right is positive roll. That is the positive rolling moment. Now, similarly, right aileron up, left aileron down gives you a positive rolling moment, right? Because if you have your wings like this, if you deflect the aileron on the left wing down, you have more lift generated. Here you have less lift and it rolls towards the right. Okay, so right aileron up, left aileron down. This configuration gives you positive rolling moment. Okay, now for static lateral stability, and for a positive roll, you need CL. Okay, this should have been CL beta. CL beta to be less than 0. Okay, so following similar configurations, same pattern, you have the equation for CL beta in this manner, right? It's the same force that is responsible for rolling also. Now, can you tell me what should CL delta A be? CL delta A. CL delta A is dou CL by dou delta A. So for a positive aileron deflection, that is left aileron down, right aileron up, will the rolling moment be positive or negative? So positive aileron deflection is right aileron up, left aileron down. Will that create a positive rolling moment or a negative rolling moment?
Positive, ma'am.
Positive. So this quantity will be what? Will be greater than 0 or less than 0?
Greater than 0.
Greater than 0. Exactly. So the answer to this question, both are positive. Okay. So that would be this option. Right? Let's move on. Okay. Now we move on to week 6 contents. So can anyone try to recall what was the condition for less takeoff speed, for reducing the takeoff speed? So takeoff speed equation was the takeoff is 1.3 times V. The criteria for reducing this takeoff speed be?
Reduce Vstall speed.
Reduce Vstall. Yes. So what is Vstall formula? Do you remember?
Under root of 2
Under root-
WS by rho CL.
The root of
2
Twice of wing
W
loading upon
CL max.
rho CL.
CL max.
So what could be done to reduce this V takeoff?
Reduce wing loading or
Reduce wing
increase
loading,
CL max. Increase CL max.
increase CL max. Exactly. So these are the conditions. The reduce wing loading. You can either reduce the takeoff weight or increase the wing area. Denser air. So that is depending on the location of the runway, and increase CL max. To increase CL max, we can have these better airfoil designs, cambered airfoils, different airfoil designs, or we can have flap deployment. These are called high lift devices. We can have flap deployment. So we can change the CL max when required. It won't be throughout the operation of the aircraft. Okay. So depending on this, in hill stations, will you have shorter or longer runways? Hill stations have denser air or less dense air?
Less dense air, so we will have longer runway.
Exactly. So you will have longer runways. Did everybody understand that? Did anyone not follow why it should be longer runway? Okay. Just let me know if you don't follow anything. Similarly, to increase the rate of climb, what are the criteria? So rate of climb equation, we know we begin with this. So this is the power available and this is the power required. So the difference of them divided by the weight gives you the rate of climb. When you substitute the drag equation, you get this quantity here. And just manipulation of these terms gives you this final expression. Okay. So from these expressions, we can see that to increase the rate of climb, increase this rate of climb, you can reduce the wing area, reduce the drag, or you can increase the thrust to weight ratio, or you can increase the aerodynamic performance or aerodynamic efficiency. Okay. So these are the different parameters that you can change the rate of climb, right? To increase them, you reduce wing area, increase thrust to weight ratio, or increase CL by CD. Okay. So now let's look at a few questions. At ideal cruise condition, thrust loading is equal to drag to lift ratio, is it equal to drag to power ratio, is it equal to lift to drag ratio, or aerodynamic efficiency? What is aerodynamic efficiency? What is the formula?
CL by CD or L by D.
L by D. CL by CD. Correct. Okay. So what is the correct answer here?
Lift to drag.
Let's take lift equal to weight, thrust equal to drag. So these two option C and D are the same. Okay. Lift to drag ratio. So let's continue with this. At cruise, you have lift equal to weight, thrust equal to drag. So if you take thrust to weight, we have drag by, you divide this by weight on both sides, right? So divide by weight, you get, replace W with L. So you see thrust loading is equal to D by L. That is basically 1 by aerodynamic efficiency, right? So thrust loading is D by L. So it's drag to lift at cruise, right? Yes, or it is 1 by aerodynamic efficiency. Okay. Next question. If the weight of an aircraft is increased, then thrust loading will, simple question, what would it
Degrees.
be? Decrease. Right? Did everybody get that? It's very simple, right? Thrust loading is nothing but T by W. And if weight of the aircraft is increased, this overall term will decrease. Very simple. A typical jet airliner has cruise thrust to weight ratio of 0.5. So let's write that down. Thrust to weight ratio is 0.5. Determine at which aerodynamic efficiency the airliner is flying.
2.
Exactly. So thrust to weight ratio we just saw is L by D. Sorry, it's D by L, which is nothing but 1 by L by D. So that is 1 by 0.5, which is 2. And L by D is your aerodynamic efficiency. If the weight of an aircraft is 875 kg and lift to drag ratio of the aircraft is 13, the aircraft is flying at a speed of 57 meters per second. What is the thrust required to power required ratio at cruise condition? Okay, so let's try to do this. So you have, let's write down the questions. So weight is 875 kg into 9.81. Lift to drag ratio is 13. And it's flying at a speed of 57 meters per second. Okay. So now we know it's at cruise. So thrust to weight is nothing but drag to lift. So you can get thrust here. That is 1 by L by D. W by L by D. W is 875 into 9.81. And this is 13. What is the value?
660.
660. 660. 660 what? What is the unit?
Newton.
Newton.
Now let's try to calculate power required. What is power required?
V infinity into T.
Yes.
Into V. So you have 660 into 57. And that gives you, what is the value?
37,620 watt.
37.62 per kilowatt.
Yeah.
So they've asked you the ratio of thrust required to power required in kilowatts. So it is 660 by 37.62. What is the value?
17.54. Option B.
That's the correct answer. Okay, you could have just actually we could have just done 1 by 57 into 1000, right? Because yeah, we could have done that.
Ma'am,
Yes.
how does it, ma'am? Plus 660 by 37.62, ma'am. Thrust is in Newton.
Yes, thrust is
Power
in.
of watt. It is
So,
kilowatt, ma'am. So shouldn't it be divided by 27,600?
so we have got our answer in 37,620 watts, which is nothing but 37,620 kilowatt. The question says thrust required in Newton to power required in kilowatt.
Okay, okay. Then got.
So an aircraft has lift to drag ratio during cruise as 2.5. If drag is 2.5. Load factor is 1.2. What value of thrust loading should be selected? How do we go about doing this? The thrust loading is E by
T by
W.
W.
That is 1 by L by D. So initially at cruise, your lift was equal to weight. But now you have that load factor. So you have,
N times W.
yes. So if this was initially W, we replaced it with L, right? So if it was thrust equal to drag divided by weight, and then you had 1 by W by D, right? So if you replace W, W is L by N now. It's not, W is not equal to L. So you have 1 by L by D by N. It's nothing but N by L by D, right? So this is the final thing. 1.2 by 2.5. Is this clear how we came to this equation? So you had thrust equal to drag. You divided by weight on either side. You replace the weight with lift for the first case. Now you have weight is equal to L by N. So you replace that here and you get the final equation. So 1.2 by 2.5.
0.48.
That is the right answer. Moving on. As a designer, I want to reduce the empty weight of my aircraft. Therefore, I will increase wing loading, decrease wing loading, or wing loading has no effect. Straightforward question.
No effect, ma'am.
No effect?
I think decrease wing loading.
Decrease wing loading, right?
Sorry. Yeah, decrease the wing loading W by S.
I want to reduce
So-
wing loading. If I want to reduce the weight, I reduce the wing loading, right? Which one is that? D. Okay. Thrust loading during flight does not remain constant. Why? Because it will not change. Ignore this option. Fuel is not burned at all. Fuel burns with each mission phase. None of these.
Third option, ma'am.
Third option, yes. Climb performance of an aircraft improves by, we just went through these points, rate of climb. So will it improve by lowering the weight, lowering the drag, or increasing the thrust?
ABC.
Everything. So what was the formula? Let's just go back to that slide. So what? It has W, it has thrust, and where the drag is here. Okay. So you can just see it directly from this equation. Actually, you increase the thrust, reduce the weight, reduce the drag. It increases the rate of climb. That is how you improve the climb performance. So what was it? Rate of climb is PV minus dV by W. Lower the weight, lower the drag, and increase the thrust. All of these terms contribute towards improving the climb performance, improving the rate of climb. Okay. What will the excess available power of an aircraft determine? Will it determine levels of flight performance, gliding flight performance, or climbing performance?
climb performance.
Yes. Again, same equation. Rate of climb is PV minus dV by W. This is power available, so it's power available minus power required by weight. Power available comes from your power plant, and power required is the drag that is associated at that condition. Okay. Okay. To improve the climb performance of an aircraft, which one of the following is the correct combination? We just went through this. What would be the right answer?
Lower weight, lower drag,
Four.
higher force.
Option 4.
Yes. Lower weight, lower drag, higher thrust. Yeah, these are the equations which we use to come to that conclusion. For a conventional aircraft, the load factor during descent will be, load factor is L by W. For descent, what will it be?
Less than 1.
Less than 1. Okay. Okay, so we'll come back to our neutral point calculation. And I think we should start with a simpler neutral point equation derivation, because last time it got a little complicated. So let's start with the simple case of just one wing and one tail. Okay, so assume this is your CG location, this is your neutral point location, and the distances are measured from the leading edge of the wing. So you have the aerodynamic center of the wing here, CG, neutral point, aerodynamic center of the tail here. Okay, so let's proceed with the derivation. We start by taking M at CG. What is the moment at CG? This is the cambered airfoil, this is a symmetric airfoil. Okay, so what is the moment at CG? CG, what is the equation?
Lift due to wing
Okay,
and distance to CG, XCG.
into
XCG.
XCG. Okay, so where is the lift at the wing acting?
Oh, sorry, ma'am, it will be XCG minus XACI.
Yes, XAC, the wing.
Yeah.
Okay, then
Movement around the AC of wing
yes, so MAC wing. Then
minus lift due to tail,
yes,
and the distance is XACT minus XCG.
okay.
And then MAC of tail minus.
Okay, so it's a symmetric airfoil, so we'll just, but yeah, you're right. You
Okay,
should have
0. It
AC
will
of
be
tail,
0.
and this goes to 0 because it's a symmetric airfoil. Okay, so now we divide throughout. You divide throughout by
Q infinity S C bar.
okay, half rho V T C bar. Okay, divide throughout by that, you get CM at CG. We'll continue calling it CM. So you have, what do you have here? You have,
Only CL,
so it will be CL naught plus
CL naught plus CL alpha
into
multiplied by this XCG minus XAC divided by C bar.
divided by C bar. Then
CMAC wing
CMAC wing
minus
minus
CL naught will be 0 for the symmetrical. So
correct.
CL alpha of tail,
Yes,
and then I guess it will be alpha W minus IT.
W. Okay, so I'll just write alpha tail here for now.
Okay.
Yeah, you're right. Alpha W minus IT. Yes. X
Into XACT minus XCG divided by C.
divided by C bar. Okay.
I think, ma'am, there should also a ratio come of S of
Yes, yes, yes.
tail
There
upon
should
S
be
of wing.
ST upon S. Okay. So now IT, alpha tail, you represented by alpha wing minus, it should be plus I tail if you're taking this direction, okay? Plus I tail, and there will be one minus downwash component.
minus epsilon.
Yes. And that epsilon is,
Downward angle.
so yeah, it's a downwash angle. It's represented linearly. If you take a linear
Epsilon
variation.
naught plus d epsilon upon d alpha into d alpha.
Okay. Yeah, you need to remember that it is d epsilon upon d alpha wing. Okay. So that is where even I had made a mistake during the derivation initially. So keep this in mind. Now, if you substitute this into these equations, you have Cm naught. So Cm equals Cm naught plus Cm alpha into alpha wing. Okay, so we'll write each of those terms separately. Cm naught is what?
CL naught xcg minus xac upon c bar.
C bar. Yes.
Plus CMAC of wing.
C of the wing. That's it, right? Is it?
Yes.
That's all?
Should be.
So this alpha tail has all these components, right?
Yes, ma'am. Yes, its term also will come.
Okay. So you will have minus
ST upon S
S
CL alpha T
then we have-
alpha W.
alpha W will come in the Cm alpha part, right?
Okay, yes, ma'am. Yes. I see.
Minus epsilon naught into the moment arm. XAC tail minus XCG by C bar. Okay. Similarly, for Cm alpha, can someone else try this time? Cm alpha, all the half the terms we have represented in Cm naught. What are the remaining terms? Can someone else try this time? This is the main equation. We have taken all terms that are independent of alpha, right? Alpha wing. Now we'll take all terms that depend on alpha wing. Can someone try? We've already taken half those terms, the ones that are independent of alpha wing.
CL alpha.
Yes, Cl alpha. So, and the momentum will come, right? XCG minus XAC wing by C bar. Next, what will be the next term?
Plus CL alpha.
So this term is done, right? So this term is done, this term is done, this term is done. What is remaining? You're right, just continue. So the wing contribution is done. Now only tail contribution is remaining. What terms in the tail angle have alpha wing? So just look into this. Only that term. Can you tell me? Okay, let me just write it down. Tell me if I'm wrong. C upon S, Cl alpha tail, and then you have, what are the terms remaining? You have alpha wing. We have 1 minus dou epsilon upon dou alpha of the wing into XAC tail minus XCG by C bar. Is this right? Okay, let me just write that down again. Cm alpha is Cl alpha. Now, how do we find out the neutral point from this equation?
putting CM alpha equal to 0.
Exactly. So for neutral point, or if you're CL alpha of the tail, X AC of the tail minus X neutral point by C bar 1 minus dou epsilon by dou alpha wing. Okay. From this, what will neutral point be? Just take all the terms with neutral point on the right hand side or on the left hand side and just try to find out this. What will it be? Try. So I'm just representing. So if it's X NP by C bar is X bar NP, X AC wing by C bar is X bar AC wing, and X AC tail by C bar is X bar AC tail. Okay, this is just for simplicity. So X AC wing plus you have ST upon S CL alpha of the tail X bar AC tail 1 minus dou epsilon 1 dou alpha wing, the whole divided by CL alpha wing plus ST upon S CL alpha tail 1 minus dou epsilon by dou alpha wing. Is this right? Just verify this for yourself. Just try deriving just this equation from this to this. Just check. Just look into it and let me know if it's right, or if there's any mistake, tell me where I've made the mistake.
Ma'am, 2 minutes still look okay.
Okay. Anyone else? Any mistake, or if it's okay, we can move on. Okay, so I'm guessing there is no mistake. Let's move on. So what you can see from this equation is that the neutral point location is like a weighted average of the CL. So if you look at it carefully, it's the lift of the wing into the weight, into some weighted component. So it's like a weighted average. Weighted average. Okay. So some components. So if you have so this X bar, okay, it's X bar NP is CL alpha of the wing into some weight plus CL alpha of the tail into some other weight by CL alpha of the wing plus CL alpha of the tail. If you take this entire term to be the CL alpha of the tail. So that weight is nothing but this location. So when you find out the center of gravity of multiple masses attached together, you do something akin to this, right? So I'm not saying that it's an exact weighted average, but it's something like that. That is how it helps me to remember. So I think you should go about looking at it in that way. It's like a weighted average of the distances. This W1s are the distances. Okay. Okay. So now let's proceed with our previous. Let me just go over this again. So you have two wings, one high wing, one low wing. Let's take wing 1, wing 2. You have a canard. You have a tail with a negative tail setting angle. And we assume the CG to be here and neutral point to be here to make it stable. Then they've given you the distances 1.5 meter from the tail of the canard to the leading edge of the wing. And they've given you 0.5 meters from the tail of the wing to the leading edge of the tail. Okay, from the trailing edge to the leading edge of the tail. Then they've given you some aerodynamic and geometric parameters here. Like we discussed last time, the wing is cambered. The canard and tail are both symmetric. So what does that mean? CM at the AC of the canard and tail will be what? For a symmetric airfoil, what will it be?
0.
0. Okay. Then they've given you the spans of the wing, canard and the tail, or the Oswald efficiency factor, the root chord, the taper ratio, and I had forgotten to mention the taper axis. This is mid chord. This is trailing edge. And what will be the taper axis of the tail? What will be the taper axis of the tail? Okay, let's see. If your canard has a taper ratio of 0, what is the shape of the canard?
Triangle.
I can't hear you. Can you be a little louder?
Triangular.
Triangular, yes. So canard is triangular. What about
Tail rectangular.
rectangular? So what?
Rectangular, ma'am.
Yes. So there is no taper axis because it doesn't taper, right? Okay. Now let's move ahead with the derivation. So I've just made another figure which gives you all the distances from the leading edge. What is given in the question is this distance and this distance. Okay, we'll use it for the calculations, but for the derivations, we'll just use these terms and we'll move ahead with the derivation. Okay. So now one of you tell me, what is MCG? We did it for the simple wing and tail configuration. Now we'll have canard, 2 wings and 1 tail. Both the wings have similar airfoil cross sections and dimensions. So now what is MCG? Moment at the CG. Tell me. Tell me what is the moment at the CG? Come on, one of you just try. We just did it for the wing and tail. Start for the wing and tail. What is the contribution? What is the moment contribution at CG due to wing 1? Let's start with wing 1. This is wing 1, wing 2, this is canard, this is tail. Let's start with wing 1, like the previous section. What was the first term?
Lift off.
Lift. Are the others listening? Am I audible to everyone? Can you tell?
Yes, yes, ma'am.
Yes. Okay, good.
Listening and understanding.
Okay. So can someone else tell me what is the first term contribution of the wing 1 towards CG moment? It is the lift. So what is the
L into XCG minus XACW.
CG minus SCW. Okay. Next. So since both the wings have the same cross section, same airfoil, I'm just going to take twice. Okay. Okay. Next. Next term will be?
I think the contribution of the tail.
Is the wing contribution done?
Okay, we will also have to consider drag portions.
Okay, yeah. Tell me the drag portions. If this distance is let's CG. Let's CG. Yes, tell me. He's right. Drag portions. What will we do? drag on wing 1 into, what is the moment arm?
CG, ZZCG.
Okay. Similarly, for wing 2,
It will be minus D1, DW2. Yeah,
into ZCG.
ZCG.
And since it's the same airfoil, both these terms will cancel out. So it will
Each
cancel
other.
out.
Yes.
Yes. Next,
Now we'll move to tail.
okay, tell me the tail contribution.
That will also give negative, I guess.
Yes. Negative
T into
into
XACT.
ACT. That's it. We need this distance, right? This distance.
Minus XCG.
Exactly. CG. Then what is the next term? What is the next contribution? Are we done?
Then we'll move to canard.
Yes. Tell me the canard contribution.
It will be LC,
Let's see.
the lift on the canard, multiplied by XACC.
CC. Again, it is the moment at the
Plus,
CG.
plus,
Yes.
plus XCG.
CG. Are we done? All the is the moment at the CG completely taken care of? Is it done? Okay, there is one term missing. Can you tell me what it is? What is missing?
I think whatever forces are shown here, we have accounted for them.
Okay. Okay, it's not a force that is shown here, but the wing is a cambered airfoil. Can you try to get something from that? Both the wings are cambered. Does that help in any way? Something in the chat box. Zero lift moment about AC, exactly. So you have two moments here. Okay, so you have plus Cm AC of the wing. And since both the airfoils are same for the wing, I will just take 2. Now, similar to the previous derivation, what is the next step? What is the next step? What is the next? We just did this derivation. Let me go back to that. So what is the next step? We have done till here, right? This is taken care of. What is the next step? Right there on the screen. What is the next step?
Um, Not getting this.
Okay, so you need to divide this equation to get the non-dimensional parameter, right? Divide the equation by half v square SC bar.
Okay, dynamic pressure.
Yes. Dynamic pressure and these terms. Dynamic pressure is just half rho v square, right? divide by half rho v square s c bar. Okay, so what do you get here? You get CMCG. Here, what will we get? 2 CLW. So we have CL naught plus CL alpha wing into alpha wing. Then what will be the next term? What is it multiplied by? It's right there in the equation.
XCG minus XACW. Yeah.
Then what happened to the others? Are the others not part of this? You muted yourself. Just people responding every time. We took a fairly simple derivation. I've just added 2 more surfaces. It should be simple. We're following the same pattern. Somebody else, it's always only 2 people answering. Tell me what the next term will be here.
XACC.
I can't hear you.
XACC.
XAC. Okay, so I divided MCG by half rho. Okay, so MCG by half rho V square SC bar is CMCG. Okay. If I divide lift on the wing by half rho V square SC bar, so this term gives you CL, right? So it gives you CL by C bar. So this CL is CL naught plus CL alpha into alpha by C bar. So that is what I've written here, and here there will be a C bar. Okay. Is it clear now? Is it because you're not following what? Just tell me what it is and we can go over it again if you want. I hope it's clear now, right? I just divided both sides by half rho V square SC bar. So this gives you the non-dimensional momentum. Similarly, on the right-hand side, you have CL. And I've split the CL in the linear fashion, CL naught plus CL alpha into alpha. Okay.
Yes, ma'am.
Yes.
So now tell me what the next term here will be. Let me just erase out this. Just tell me what the next term will be. There are 8
Minus
minus
CL naught T, I think it will be called,
T
plus CL alpha T into
Yes.
alpha T
correct. Then you have
into XACT minus XCG upon the mean aerodynamic curve.
and here there will be a ratio which is ST upon S. Okay. Next.
Yes, yes.
Next.
Plus will be CL naught C
Yes.
plus CL alpha C into alpha C
Yes.
multiplied by XACC plus XCG into SC upon S
Yes. What is the next term?
plus
Plus. So all of these are done. Only this is left.
yes, ma'am.
Oh, this was okay.
The
My
zero
bad
left
here.
ones.
This should have been moment. So you have 2 CM ACW. Okay. Okay. Now, similar to the previous case, we have to take terms that are dependent on alpha wing and terms independent of alpha wing. Before that, we need to split these. So this alpha tail and alpha C. Both of these terms contain some alpha wing terms. Okay, so we'll take alpha tail is what we did last time. We'll start with that. Alpha tail is alpha wing plus I tail, and we'll neglect the downwash for now. It should have been this, but we'll neglect it for now. Okay. Similarly, alpha canard is alpha wing plus IC. Okay. So if I substitute these into this equation,
Now, what exactly I is?
okay. I is the, so IT is the tail setting angle, IC is the canard setting angle. So what it means is that it is set on the aircraft with respect to the fuselage reference line at that angle. If the wing is at
Okay.
0 degree setting, if the wing was something like this, so you will have a wing setting angle also. Okay.
Yes. Okay. Got it.
So now if you substitute these terms into this equation, let's try to find out the terms independent of alpha wing. Okay. Try to tell me. So let me just try to get another color pen. Okay. So this term is independent of alpha wing. This term is independent of alpha wing. And this term is independent of alpha wing. So is this. And there are some other terms inside here that are independent of alpha wing. But first, let's write down these circled elements. Okay, so it will be 2 CL naught of the wing into XCG minus XAC wing by C bar. Then it will be minus CL naught tail into XAC tail minus XCG by C bar
Into ST upon S.
then the term will be plus
CL not C.
CL naught C ACC plus XCG by C bar into SC upon S plus 2 CM AC wing. Now here in our question, we have considered the tail and canard to be symmetric. So what happens is these terms go to 0. So there is no CL, sorry, not that. CL naught canard and CL naught tail go to 0. So this CM naught is just 2 CL naught wing CG minus XAC plus 2
Plus 2.
AC wing. So now
Ma'am,
we'll try to,
upon C bar also in the first term.
okay, yeah, let me just erase this. C bar. Okay. So now we'll try to write down CM alpha terms. So there's somewhere. Alpha tail, and alpha tail was alpha wing plus I tail into XAC tail minus XCG by C bar plus CL alpha canard into alpha canard wing plus IC, that was XACC plus XCG by C bar plus 2 CMAC wing. Okay, so we did CM naught in the previous slide. Now we'll try to do CM alpha. So what are the terms that are dependent on alpha wing? It's very simple now that I've expanded the alpha tail and alpha canard. Just tell me the terms quickly. So what are the terms that are dependent on alpha wing here? Am I audible to everyone? Why is no one responding?
Yes, ma'am, you are audible.
Okay. What are the others doing? It's very simple. What are the terms in this equation that are independent of alpha wing?
From the 2 CL naught XCG minus XAC upon C bar.
Yeah, okay. I'm sorry. Terms that are dependent on alpha wing. You're right about
Okay,
that. So it's the remaining
dependent
one,
now.
the second one, right?
Yes, so that will be 2 C alpha wing into alpha wing.
Alpha wing.
Alpha wing will not be this. So CM alpha is dou CM by dou alpha. Okay. So here it will be XCG minus
XCG minus
C wing
CC.
by C bar. Correct?
Yes, ma'am.
Okay. Next term will be
Minus
minus
CL alpha T.
CL alpha tail
Mm, alpha wing.
alpha. If you do,
Alpha T.
no, if you take the derivative of this term with respect to alpha wing, you will have minus CL alpha tail and this term, right? That's all.
Yes,
Right?
ma'am.
Yes.
Yeah.
So you have XAC tail minus XCG
XCG by
C
C
bar.
bar
Next term will be
plus
plus
CL alpha C.
CL alpha C
X alpha C.
what?
No, XACC.
XACC
Minus.
that
No,
is,
plus
yes, plus
XCG
CG by
by
C
C
bar.
bar.
Now what I've missed here is that there was a ST upon S.
By
There
S,
was a
ST by S.
So same, I will put it here, C upon S. Okay. Now to find out neutral point. So if CG equal to neutral point, CM alpha will be
0.
0. Exactly. So just write that equation 0 equal to 2 CL alpha wing X NP minus X AC wing by C bar minus CL alpha tail X AC tail minus X NP by C bar into ST upon S plus CL alpha C X AC C plus X NP by C bar SC upon S. Okay. So now we need to find out XNP. So what are the other terms in the equation? Are they known? If they are not known, let's try to find them out. Let me just write that down again. Okay, so the terms that we don't know and have to find out. CL alpha tail, CL alpha C. Then we have S, ST, SC, S, T, C, and then you have XAC tail, XAC wing, XAC tail, XACC. Okay, let's try to find this up. Previous class we had done canard. Let's start with canard. So for canard. Now, what is SC, area of the canard?
1/2 BC into CR of C, ma'am.
To BC into
CR of C.
CR of C. Okay. So what were the values? Right? Just tell me the value. 0.2.
Ma'am, 1/2 into 1 into 0.
Okay. Okay. So next is, so our canard was a triangular configuration, right? It was like this. Span is BC and CR. So this was 0.5. This was 1. So if your C bar is somewhere here, okay, let's find out C bar. C bar of the canard is, what was the formula? Aerodynamic center, what was the formula?
2/3 CR of lambda 1 plus lambda plus square by 1 plus lambda.
Now what is lambda here?
Taper ratio is equal to 0, ma'am.
0, exactly. So it will be just 2/3 into 0.5, which is
0.33.
so it's 0.33. Okay. Then we need this value. We need this value. So XAC of the canard will be, what was it? The entire thing is CR. CR minus C bar. That's it, right? CR minus C bar plus,
Yes, ma'am.
okay, plus the aerodynamic center is somewhere here, right? 1/4 quarter chord point. So what would this value be? This is your aerodynamic center. What is the value of the aerodynamic center from the leading edge? So this value is CR minus C bar. And what is the small value? What is that value? Did you understand how the blue line is CR minus C bar? Did you understand how the blue line is CR minus C bar? Or do you want me to explain it again?
Understood, ma'am.
Understood. Okay. So what is the purple line? This small quantity?
CR plus
That small quantity is nothing but the quarter chord point, right? So it's just
yes,
CR
ma'am.
4. Yes?
Yes, ma'am.
Yes. Okay. So let's try to find out that value. CR is 0.5. Okay, till where was it last audible?
Until you have told us about the quarter chord point, the purple disc.
Okay, okay. So I'm sorry about that. So I just substituted the values and found out that it is 0.25. Okay. Okay. So now what we know is this is for the canard. So from the leading edge of the canard till the aerodynamic center, this value is 0.25. But what we need is XACC, this entire distance. So what will that be? This is like some XACC prime, okay? So what is XACC? So we know this distance. We need to know this distance. What will it be? Let me just draw it clearly again. So what we have found out.
Ma'am, 0.25.
Yes.
Uh,
Yes. What is this? And in the question, this value is given to you, yeah, right? How much is the value? 1.5. So this is given as 1.5 meters. So what do we have to find out? Simple
so the
geometry.
distance, ma'am, the distance from the trailing edge to the line, ma'am, vertical drawn.
So distance from trailing edge to the vertical line is 1.5 meters, correct? That's given in the question.
Ma'am, I think so. It is from leading edge, ma'am.
So this is what is given in the, where's the question? Yes. So from the trailing edge of the canard to leading edge of the wing is given in the question. Right?
Ma'am,
Little neat, okay?
excuse me, ma'am.
Yes, yes. Tell me.
Ma'am, just can you show the figure once again, ma'am? Because I'm getting confused, ma'am. Whether is it from trailing edge, ma'am?
1 minute. 1 minute, just a minute, okay? So this was the question, right? It is from trailing edge. The trailing edge of the canard to leading edge of the wing. Is it clear now?
Yes, ma'am.
Yes. So what I've written, where is it? What I've written here is correct. .5 meters from the trailing edge of the canard to leading edge of the wing is given in the question. Is that okay? Is that okay?
Yes, ma'am.
Okay. And this 0.25 meters, we have found out from the leading edge of the canard to the aerodynamic center of the canard. So if this is the aerodynamic center of the canard, we know this distance. Right? What we need is this entire distance. How do we find out that? How do we find that out? So
Which
what we
one,
need is
ma'am?
this small distance. What is this distance in blue?
Ma'am, 1.5 meters minus, no.
So what is the overall chord, the root chord of the canard?
0.5, ma'am. 0.5 meters.
So it will be 0.5 minus
Plus
0.2.
ma'am, 0.25.
Is this right? The line in blue?
Yes, ma'am.
It will be plus 1.5, right? So overall the value will be
1.75.
So it will be 1.75 meters. Okay. So we have found out SC, XACC. Now we need CL. These are the terms that we need to find out. We have found out SC, XACC. Now let's find out CL alpha of canard. CL alpha of the canard. This is in 3D. So CL alpha of the canard in 2D by 1 plus CL alpha 2D by pi EAR. So what is aspect ratio of this canard? AC square by SC, which is
B by C.
yeah. What is the numerical quantity? It won't be B by C, right? That's only for triangle. So in this case, it will be 1 by 0.25, which is 4.
Yes,
Correct?
ma'am.
Okay. So now let's find out this CL alpha 2D of the canard was 5 and Oswald efficiency factor was 0.8. 5, 1 plus 5 by 5 into 0.8 into aspect ratio is 4. How much is this value? 5 divided by 5 divided by 0.8 divided by 4 plus 1. 3.33. Am I right? Just verify my answers.
Yes, ma'am. Same, ma'am.
So we have also found out CL alpha. This, and so now let's do the similar calculation for the tail. Now tail is rectangular, so it's fairly simple. Let's do it for the tail. S tail. What is the area of the tail? CR of the tail into B of the tail, which is value was what? The CR of the tail was 0.3 and span was 1.5. That is 0.45.
0.45.
Next, let's find out the aspect ratio. It will be B of the tail by ST. B of the tail is 1.5 square by 0.45. This is
5.
So now let's find out C bar. the tail. It's just
It is
2 by
rectangular, ma'am, so it will be same.
okay, yes. Okay, so C bar is done. And the XAC wing will be C bar by 4. What is the value? What is the value?
Ma'am, what was C bar value?
C bar was CR, right? It's 0.3.
0.3, ma'am.
Yes. So
Ma'am,
what is the
answer
final?
is
0.075.
0.075.
0.07.
Next, what do we have to find out? What else is left? So we have found out this. We have found out this CL alpha of the tail. CL alpha of the tail is CL alpha of the tail 2D upon 1 plus CL alpha of the tail 2D on pi E AR. So that is 4 and E is 0.7. 4 by 1 plus 4 by pi into 0.7 into 5. This is
2.933.
9.
2.933.
Okay, let's leave it at 2.9. Let's do it for the wing now. Wing. Okay, so the wing says, what does it say? The taper axis is mid chord, the root chord is 1, and the taper ratio is 0.5. So CT upon CR is 0.5. CR is 1, right? Will be CT will be 0.5, right?
Yes.
Yes. So how will the wing look? Taper axis is mid chord. Okay, so how will the wing look? This is your CR. Be something like this.
Yes, ma'am.
Okay. So now let's find out the area of the tail. Area of the wing, sorry. What will it be? We did a similar question, I think, just sample problem. So let's divide the areas. Okay. So I think I have, yeah, the table is here. So span, yeah, so span of the wing is 4 and the root is 1. So this 1. Of the rectangle will be 4 into 0.5, right? Then it will be the area of this triangle, this area. What will it be?
Half into 4 into height is
1 minus 0.5, right?
yes, 1.5.
And there are 2 such triangles.
2
So
so multiplied by 2. Yes.
what will be the final answer? 4.
4.
I'm getting 4. Okay. Next, what do we have to find out? Aspect ratio. Aspect ratio of the wing is B wing square by S wing. B wing was 4 by 4, so it's 4. Then we needed CL alpha of the wing. So what was the CL alpha? 6 and efficiency factor was 0.9. So it is 6 by 1 plus 6 by 5 into 0.9 into aspect ratio is 4. What is this value?
3.92.
So now we have found out all these quantities. We'll just substitute it into this equation. Okay, I'll just write that down again. 0 equal to CL alpha wing CJ minus XSC wing. Okay. Out was this was the tail, right? So what we have found out is this small quantity. That is 0.075. What we need is this entire distance. So we need to add plus this distance, which is given in the question as 0.5 meters. Okay. Is that right?
Yes, ma'am.
0.575. What was the equation? By C bar minus CL alpha tail NP. Neutral point by C bar plus CL alpha canard XACC plus XNP by C bar ST upon S C upon S. So now let's substitute all these values. CL alpha of the wing was 3.92. 3.92 into XNP minus XAC wing is, okay, we didn't calculate that. Okay, so let's try to do what is C bar.
Ma'am,
Tell me.
ma'am, I'm having a doubt, ma'am.
Yes,
This
please ask.
CL alpha W is equals to 6 by 1 plus 6. How did you get the value 6, ma'am?
Okay, 6 is, okay, I did not write that equation down. Let me just do it again. So it is CL alpha wing by 1 plus CL alpha wing by pi EAR. That is 6 by 1 plus 6 by 5.9 into 4, which is 3.92. Okay. That 6 is given in the question, CL alpha.
Got it, ma'am.
And now let's try to find out C bar. C bar formula was 2 by 3 CR 1 plus lambda square by 1 plus lambda. What is this value?
2 by 3 CR is, ma'am, 1, ma'am.
CR is 1.
1, ma'am.
Final answer. Can you tell me the final
And
answer?
yes, ma'am.
I'm getting 0.7. Just correct me if I'm wrong. Is everybody getting 0.7?
Ma'am, doing ma'am.
Okay, okay. Are you getting 0.7?
Yes, ma'am.
0.7. Okay. So now let's find out what is this XAC of the wing. So C bar we have found out as 0.7. This small distance is C bar by 4. But we need the quantity from the leading edge. What will it be? It will be CR minus, it will be CR by 2 minus C bar by 2 plus C bar by 4. Am I right? So this quantity is CR by 2, right? This quantity is C
हाँ
by
परमानेंट
2.
है वो, मतलब अभी वेबसाइट पे देखो तो
Okay. Is this clear?
Ma'am, can you once again explain?
Yeah. So I'll try to take a different color pen. So this is your mid chord. And this is your leading edge. So this distance, what is this distance?
CR by 2.
CR by 2, correct. And this is your chord. What is this distance?
C bar by 2, ma'am.
Okay. So CR by 2 minus C bar by 2 will give you this distance, right? This quantity minus this quantity gives you this value here. The line in purple is what? This quantity is the line in purple, right?
Yes, ma'am.
Okay. And then if you add this C bar by 4, which is given here, you get the XACW.
True.
Correct?
Yes, ma'am.
Okay. So XACW, what is the final value? CR by 2, that final
0.
value.
Uh, 0.5, ma'am. CR by 2 value, ma'am.
No, this entire thing, XAC, what is the value? I'm getting 0.3. Is this right? Can you check if that's right? Just circle the quantities that we'll be using. Okay. Is this 0.3 right? I'm just going to go ahead presuming it's right, okay? Okay. So XACW was 0.3 C bar of the wing, 0.7. Minus CL alpha of the tail was 2.9. Alpha of the canard was 3.33. To XAC of the canard was 1.75. MP 5.77. SC is 0.25. And S is 4. Okay. Now the only unknown in this equation is XNP. Can you try to find out what is XNP? You try it?
Ma'am,
Yes.
for finding out the XACW of the
Yes.
wing, ma'am, we did
Yes.
CR by 2 minus C chord of C, by 2 plus CR by 4, ma'am.
C bar by 4. Yes.
Ma'am, I'm getting answer as 19, ma'am.
Why? How will it be 19? It has to be less than the CR, right? So it will be. Let's try doing it. So it will be 0.5 minus 0.7 by 2 plus 0.77 by 4. How much will that be? Achit?
Ma'am, that is what I'm getting answer as 19, ma'am. 19 point.
How will it be 19, Achit? It has to be less than 1, right? Point 0.77 by 4
Yes,
is,
ma'am. Got it, ma'am.
so it's 0.3, right?
Yes,
0.3.
ma'am. Yes, ma'am. Yes, ma'am.
So, yeah. So in this equation, try to substitute all the, we have substituted all the values, try to find out X and P. Negate this 0.77 multiplied by 0, so that's done. Let me try to simplify this equation.
Ma'am, we'll show you its answer in next class.
Okay, let me just finish this. Even this was left previous time also. Let me just finish this. $1.176. So there's also seven plus 2.9. Okay. So, one, two, 208 XNP. Now, can you try to simplify this? Just quickly, I just want to be done with this question, at least in this class. Minus 1625 equal to 0. So XNP equals four 0.03 meters. Correct? You can verify these answers later. I've just calculated it quickly. So if it is 0.14, an XAC of the wing, so it will be somewhere here, right? XAC of the wing was 0.3, so it will be ahead of the XAC of the wing. So this is not a stable configuration, right? You can verify these answers. So this is the value. Okay. So if it's wrong, you can tell me in the next class. Are there any other questions? I actually wanted to discuss one more question, but okay. Are there any other questions? Any doubts, any questions?
No, ma'am.
No,
ma'am.
okay. So then we will meet in the next class on Tuesday. Meanwhile, if you have any queries, do use the forum. So one of us will respond. So good luck for your quiz and a very happy Holi to all of you. We'll meet
Thank you,
again
ma'am.
next.
Same to you.
Thank you, ma'am. Same
Thank
to
you.
you.